Imagine yourself standing inside a vast, shadowy tunnel, where the walls surrounding you are as unyielding as frozen stone. The only illumination is a faint glow from the distant mouth of a volcano, which spews molten rock from the planet's core directly into this passage. At your feet, you can just discern a pipe stretching toward the tunnel's exit, radiating a humid warmth that suggests hot water is flowing within, carving this very channel through the ice all the way from the crater to the world outside. Your hunger is a sharp reminder of the long journey it took to get here. Near the volcanic vent, you spot colonies of segmented worms, colored in white and red. Plucking one to taste, you find it surprisingly palatable, a potential food source for your survival here on the alien world of Iceheim. This is where we will commence our investigation into hypothetical life on ice-world exoplanets, beginning with our model of Iceheim, a planet whose straightforward structure makes it relatively easy to analyze. The planet can be pictured as a layered sphere, much like a celestial layer cake. Deep in its heart rests a core of heavy elements like iron and nickel, which is enveloped by a layer of lighter materials, analogous to Earth's rocky mantle and crust. Above this solid foundation sits a substantial layer of water, capped by a gaseous atmosphere. This basic stratified model allows for numerous variations depending on the state of its water. An ice world, such as Iceheim, emerges when this water layer freezes solid, right down to the planet's crust. If, however, only the surface freezes over a subsurface liquid ocean, we get a world I will explore in detail in Chapter 7, which I call New Europa. Should the planet's surface be entirely submerged in water without any land, it becomes a complete water world, similar to Neptunia, our subject for Chapter 8. Finally, a planet featuring both stable continents and oceans over billions of years would be an Earth-like world, the focus of Chapter 9, and would closely resemble our home. It is crucial to grasp that the divisions between these planetary types are quite fluid, a point to which we will frequently return. If Earth's oceans froze over, it would shift from an Earth-like world to one resembling New Europa. Should they freeze all the way to the seabed, our planet would effectively become another Iceheim. With those essential clarifications made, let's now delve into our first and simplest water world, one where the entire outer water layer is frozen solid down to the crust. We've given this world the name Iceheim because its vast frozen landscapes bring to mind the epic sagas of Norse and Viking life on our own planet. The very name, ending with the suffix -heim, suggests that a planet of this kind could potentially serve as a home for intelligent life. But could such a world actually exist? As I established in Chapter 1, from a statistical standpoint, nearly any conceivable world that doesn't violate the fundamental laws of physics should exist somewhere within the Milky Way. Our hypothetical Iceheim does not defy any known physical laws. In fact, planets like it might be quite prevalent throughout our galaxy. This idea becomes more plausible when you consider how the planets in our own solar system came to be. They formed by accreting material from a flat, rotating disk of gas and dust that orbited the young sun. In the inner solar system, planets were built from a mix of materials, from heavy metals like iron and nickel, to the lightest gases such as hydrogen and water vapor. During the formation of these planets, the constant meteorite bombardments delivered so much energy that their surfaces melted into a hot, dense magma. In this molten state, the heaviest elements, primarily metals, sank to form the core, while lighter substances, which would later solidify into rock, floated to the surface. Once a planet's growth phase concluded, it started its long process of cooling down. For an Earth-sized planet, the core, or at least parts of it, can stay liquid for billions of years, whereas a smaller world like Mars cools and solidifies much faster. In our solar system today, only Earth and Venus still possess liquid cores. The cores of the other terrestrial planets have long since cooled and hardened. We therefore presume that Earth-like planets are built with cores of heavy metals that can be solid, entirely liquid, or a combination of both. It's the movement within Earth's liquid core that generates its magnetic field, and the lack of such a core on Mars explains its absence of one. As we now know, water is incredibly common throughout the galaxy. The fraction of planets where water makes up at least a few % of the total mass could be as high as tens of % of all known exoplanets. If the galaxy contains roughly 30 trillion planets, as we calculated in Chapter 1, then there could be more than 1 trillion such water-rich worlds. Any of these planets located far enough from their star would eventually cool to a point where their water layer freezes over. We have already identified several exoplanets that might be quite similar to our theoretical Iceheim. Perhaps the most compelling real-world candidate is OGLE 2005 BLG 390LB, which was found through the Optical Gravitational Lensing Experiment, or OGLE, and holds the record as the most distant exoplanet yet found. Situated in the constellation Scorpius, about 21,500 light-years from Earth, this planet has a mass roughly 5 times that of our world and a surface temperature of -218 degrees Celsius. Its discoverers fittingly nicknamed it Hoth, after the ice planet in Star Wars. So, it is important to remember that planets with a metallic core and rocky mantle, sheathed in a layer of water, liquid or solid, may indeed be a common cosmic feature. Let's return our focus to Iceheim and explore the essential characteristics of any life that might develop on such a world. For life to begin and endure, it requires a source of energy. I want to consider the potential energy sources you could find on the surface and in the interior of any planet. The most immediate one that comes to mind is the energy radiating from its parent star, which is the very source that sustains the vast majority of Earth's biosphere. Given the profound cold on Iceheim's surface, you might naturally conclude that the planet must be a great distance from its star. This isn't necessarily true, however. For instance, if Earth's atmosphere were stripped of carbon dioxide and other greenhouse gases, its average surface temperature would plummet to around -18 degrees Celsius. Our planet's surface, oceans included, would freeze over, even at its relatively close distance to the Sun. As we went over in Chapter 3, Earth has endured several periods in its geological history when it transformed into a massive snowball. These epochs came to an end only when volcanic activity pumped carbon dioxide back into the atmosphere, which initiated a powerful greenhouse effect and thawed the global ice sheet. Crucially, these ice ages never persisted long enough for the oceans to freeze solid all the way to the bottom, so our world never became a permanent ice planet like Iceheim. During these snowball Earth events, a liquid ocean always remained beneath the frozen crust, much like the one thought to exist today on Jupiter's moon Europa, though we will delve into worlds like that in the next chapter. For life on Iceheim, a far more critical energy source would be the geothermal heat from the planet's core, which is concealed deep beneath the ice. We can categorize this internal energy based on the age and size of the ice planet's core. The first subtype is the residual heat that has been retained since the planet's formation. In its early days, the protoplanet that would become Iceheim orbited its star, gravitationally capturing any fragments of matter that ventured too close. Had you been standing on its surface back then, you would have seen a perpetual downpour of meteorites, whose kinetic energy was converted directly into thermal energy. On Earth, as I've noted, this heat was intense enough to liquefy the entire planet. Once the influx of meteoritic material blended with the substance of the nascent planet, an unavoidable cooling process commenced. Here on Earth, this cooling continues even today, 4.5 billion years after our world took shape. Approximately half of the heat that emanates from Earth's interior is simply leftover energy from that original, molten state, which has yet to completely solidify. A separate source of heat hidden within a planet is the decay of radioactive elements. Some of these elements have such prolonged half-lives that they can fuel a planet's core with energy over immense timescales. The half-life of uranium-238, for example, is about 4.5 billion years, which is comparable to the age of Earth itself. Consequently, about half of the original quantity of this surprisingly abundant element still exists within our planet's interior today. Scientists have estimated that the other 50% of the heat radiating from Earth's interior is generated precisely by the decay of these long-lived radioactive elements, such as uranium-238. The amount of radioactive material present on Iceheim would be contingent on the initial chemical makeup of the interstellar dust cloud from which the planet condensed. The composition of this cloud, in turn, is primarily determined by whether it was seeded by the remnants of various types of supernovae. Stars that formed from clouds composed mostly of primordial hydrogen, what we call first-generation stars, contained virtually no radioactive elements. Conversely, you can anticipate that in systems formed from clouds enriched by several generations of stellar nucleosynthesis, the concentration of such elements will be significantly higher. Therefore, in the interiors of these systems' planets, the majority of heat is generated through nuclear decay. Our Sun is typically categorized as a third-generation star, a fact that clarifies both the high level of radioactivity deep inside Earth and the remarkable diversity of chemical elements found on our world. When we analyze both sources of a planet's internal heat, it becomes abundantly clear that the size of its core is the single most decisive factor in this equation. This is a principle we can consistently rely on when examining celestial bodies across the solar system. The dynamics of heat within a planetary core can be conveniently demonstrated with the analogy of a pot of water on a stove. When you switch on the burner, the water at first appears still, but if you place your hand near the surface, you can feel the heat rising. This transfer of heat from the burner through the water via molecular collisions is a process we call conduction. After a time, however, so much heat builds up that conduction alone is no longer sufficient to dissipate it, and the water starts to boil. Water warmed by the red-hot base of the pot ascends to the surface, transfers its energy to the surrounding air, cools down, and sinks back to the bottom. This circulation is known as convection, and it commences when the heat load becomes too great for conduction to handle by itself. If Iceheim's core is relatively small, comparable to those of Mercury, Mars, or our Moon, the planet's internal warmth will be transported to its surface mainly through conduction. The world would then cool down fairly rapidly, and Iceheim would soon turn into a cold, barren sphere. However, if Iceheim's core is larger, like those of Earth or Venus, the situation becomes much more dynamic and intriguing. Earth itself offers a prime illustration of convection in full swing. For hundreds of millions of years, rocky material within Earth's mantle has been churning, bringing molten magma from the deep interior up to the surface. Generally speaking, the larger the core, the more energy convection will transport from it. For our current discussion, however, the most critical result of this process is the creation of channels through which molten materials and thermal energy can escape to the surface. This is the very mechanism that formed the Mid-Atlantic Ridge, a vast underwater mountain range extending from Iceland to the coasts of Antarctica. The ridge itself is composed of countless layers of magma that have seeped out from submarine volcanic vents along its central rift valley and then gradually solidified. If Iceheim possesses a core of sufficient size, we can confidently presume the existence of volcanic vents beneath its ice, which is a foundational element for describing any hypothetical life on the planet. These hydrothermal vents would deliver two principal forms of energy from the core to the world above. The first is the thermal energy I've previously mentioned, which could generate enough warmth to melt the ice from below, creating vast, insulated pockets of liquid water. Within these liquid sanctuaries, it's highly probable that the same kinds of molecular interactions that initiated life around geothermal vents on Earth's ocean floor could also take place. The second energy type emerging from the planet's interior is distinctly chemical. On our world, these geothermal features, also known as black smokers, expel not only magma, but a complex stew of chemical elements that supports the vibrant biodiversity of deep ocean ecosystems, providing the foundation for entire food webs. The regions surrounding Earth's underwater thermal vents are teeming with life, from microscopic bacteria to giant tube worms, paganophores, and crabs. The metabolism of the local bacteria is driven by chemosynthesis, not photosynthesis, as it relies on methane, sulfur, and various minerals dissolved in the hydrothermal fluids. A secondary, though less obvious energy source on Iceheim would be the radiation from its host star. On Earth, the sun provides the primary energy that sustains life, but Iceheim's surface temperature is below the freezing point of water. This leads us to assume the planet is either orbiting a relatively small and dim star, or is positioned a great distance away from it. This is not an insurmountable barrier to life. It simply dictates that any organism collecting and using this energy would need to be much larger than those we're familiar with on Earth. To illustrate this, for you to gather the same amount of energy that a 1 square inch leaf receives on Earth, roughly 6 square centimeters, you would require a leaf with the surface area of a full square meter on Pluto. This scale difference, incidentally, is why spacecraft sent to the outer solar system depend on radioactive plutonium generators instead of solar panels. The panels would have to be impractically massive and heavy to function effectively. On Iceheim, any light from its parent star would be rapidly absorbed by the surface ice, and the resulting heat would likely only penetrate a few meters deep at most. Beyond light, the star might also emit particle streams as solar flares or stellar wind, much like our own sun. However, these emissions are irregular and would likely cause more harm than good to any life developing on Iceheim's surface. Nevertheless, it is possible that any surface life on this planet, if it ever emerged, could adapt to a constant stellar wind, just as terrestrial life has. Of course, such phenomena would be far less likely to impact any organisms hidden safely beneath the ice. From the vantage point of an observer within the ice sheet, the planet's energy dynamics are quite clear. Heat from the core travels up to the ice's lower boundary, moves through its thickness, and ultimately radiates away into space as infrared energy, while the upper surface is warmed by starlight. Our challenge now is to figure out how life might arise and evolve in such a setting, starting with its origin. Let's return to an underwater hydrothermal vent where, as we've established, Both thermal and chemical energy would emerge from the planet's interior. The heat would create a bubble of liquid water, which could be quite extensive. On Earth, underwater hydrothermal channels can run for thousands of miles, making a tunnel a more plausible structure than a simple bubble. Many scientists theorize that life on Earth began around such vents, and I see no compelling reason why a similar scenario couldn't play out on Iceheim. Let us assume that single-celled organisms would be the first to appear, and for the sake of this thought experiment, let's say the leap to multicellular life has already happened. Once we have multicellular organisms, we can analyze their environment to understand their potential evolutionary paths. The most significant factor is that along any hydrothermal vent, there will be zones where life-sustaining nutrients are more concentrated. This creates a clear gradient in the distribution of resources, meaning that the ability to move toward these nutrient-rich areas offers a profound evolutionary advantage. Therefore, we should anticipate that natural selection would strongly favor and enhance this mobile trait in any living creatures. Such lifeforms would represent the culmination of a long developmental sequence, where each successive stage allowed them to move slightly faster toward these resource-abundant zones. The principles of natural selection we covered in Chapter 4 would be fully met, as each step in this chain of events would confer a clear evolutionary benefit. The capacity for independent movement, much like fish in our oceans, would inherently make these organisms better adapted to their environment. However, self-propulsion is not the only viable adaptation to this zonal nutrient distribution. Stationary life forms, analogous to oysters, could evolve to place their offspring in more resource-rich locations. For instance, they might release spores that drift preferentially in the direction of higher nutrient concentrations. In this scenario, while each individual organism remains fixed, the population's habitat would gradually shift over time, depending on how quickly these resource zones themselves change. Rapid environmental shifts would likely encourage the evolution of mobile, free-swimming creatures, whereas more stable conditions might lead to the slow migration of entire colonies. It's plausible that both of these evolutionary avenues could be explored on Iceheim, resulting in creatures analogous to both our fish and our oysters. These hydrothermal tunnels would almost certainly have significant temperature gradients as well. Near a vent, the water would be extraordinarily hot. On Earth, such vents can exceed 400 degrees Celsius, kept from boiling only by the immense pressure of the ocean above. Conversely, the water temperature would plunge below freezing near the overlying ice sheet, creating a spectrum of thermal zones that would drive the evolution of diverse, specialized species, much like the difference between a tiger and a polar bear. But what could you expect to find on the surface of such a world? It's a fundamental principle that all life, whether familiar to us or not, relies on chemical reactions taking place within a liquid. Given that Iceheim's surface is devoid of any liquid, you have to conclude that life could not independently emerge there. However, scientists propose that certain life forms on our own planet, having originated at deep-sea geothermal vents, eventually made their way to the surface. It seems this sort of migration is the only conceivable way for life to colonize the surface of Iceheim. When you compare the journey life would take on Earth versus Iceheim, a crucial distinction emerges. On our world, the ascent from a geothermal vent is through a vast column of water, where the main challenge is adapting to the dramatic drop in pressure. On Iceheim, the path upward is through a formidable barrier of solid ice, a much tougher obstacle to surmount. This is where the intricacies of natural selection become paramount, as the faint energy from the parent star reaching the ice's upper layer would offer a powerful incentive for life that could manage to get there. To harness that distant starlight, organisms would face a twofold challenge: They must first physically reach the surface, and every step of that journey must offer a distinct evolutionary benefit. For example, you can envision a web of microscopic fissures in the ice, allowing hot, mineral-rich water from the vents to percolate upward, carrying microbial life along with it. If these channels reach a depth where starlight penetrates, these microbes could evolve into multicellular photosynthetic beings, echoing a key development on Earth. Crucially, it would only take one such breakthrough, perhaps at a point where the ice is unusually thin, for organisms to colonize the entire planetary surface. Once these life forms established a foothold and evolved into more complex photosynthetic organisms, they would likely spread across the whole surface, no longer tied to the thermal vents below. Their existence would be entirely dependent on the parent star's light, which presents a significant efficiency problem. Here on Earth, the conversion of solar energy is remarkably inefficient. An Iowan cornfield on a bright summer day, one of the most efficient systems we have, captures only a few % of the available solar energy as organic matter. Life on Iceheim couldn't afford to be so wasteful. Therefore, I imagine their energy-gathering structures, let's call them leaves, would be enormous by our standards, and probably jet black to absorb every bit of the faint starlight. This evolutionary path suggests that Iceheim, rather than being a brilliant white sphere of ice, might be streaked or even covered by a thin, dark film of these leaves. You would effectively have two primary energy flows on this world: heat rising from the planet's core, and starlight filtering down from above. Life could evolve to inhabit the ice itself, bridging these two sources. You can picture fibrous structures, which we might call roots, growing downward from the surface to capture residual heat, while other fibers could extend upward from the vents to draw warmth from the planet's rocky floor. If these upward and downward reaching structures were to meet, they could form vast, dark jungles suspended within the ice. Contemplating intelligent life and technology on a world like Iceheim pushes the boundaries of speculation, as the emergence of higher beings would be incredibly challenging. We understand so little about the precise conditions that led to advanced civilization on Earth that we can't be sure if they could ever be replicated there. But let's assume for a moment that intelligent life did evolve around the hydrothermal vents. Its technology and perception would be shaped by an environment utterly alien to us. The world would be almost entirely dark, save for the rare glow of lava from a fissure, meaning their vision would likely operate in the infrared spectrum. Furthermore, they would need an exceptionally refined sense of touch to interpret the subtle movements and pressures of the water around them. Even though they would inhabit a liquid realm, you can picture their entire world as being confined beneath a massive dome of solid ice. The sheer size of this dome, which would represent the absolute boundary of their universe, would be determined by how much heat was escaping from their home crater. Greater heat output would mean more melted ice, which in turn would create a larger living space for any potential life. Should enough heat rise from the planet's interior, the tunnels formed by hot water could widen so much that they would start to merge. This process could create a substantial layer of water surrounding the planet's core, which would itself be encased in an outer shell of ice. A world with a subsurface ocean would thereby come into being, a concept we will explore further in the next chapter. And this possibility highlights the fluid nature of the boundaries separating different kinds of water worlds we've already considered. In this theoretical world, life would be entirely dependent on the temperature gradient between the hydrothermal vent and the surrounding ice wall or ceiling. Consequently, You can see how thermodynamics would almost certainly be the first science to emerge on Iceheim. Their earliest engines would likely generate power by harnessing this temperature difference, in a way that mirrors how humans leveraged wind energy by constructing windmills. For Iceheim's technology, the management of heat flows would be of supreme importance, likely occupying a role comparable to the control of water movement in humanity's first agricultural systems. Lacking any access to fire, our hypothetical organisms would have to depend on the heat emanating from the hydrothermal vent. For instance, they would need to channel this geothermal energy to warm their shelters if they wanted to build a civilization near the ice sheet. When it comes to materials and tools, the inhabitants of Iceheim would face a situation quite similar to our own distant ancestors on Earth. You'd expect their tunnels to contain an abundance of stones suitable for crafting primitive implements. Near the hydrothermal vents, they would also discover deposits of various minerals that could be mined and processed. Without fire, metallurgy on Iceheim would have to develop along a completely different path than ours. There is, however, a chance their engineers could figure out how to fashion tools from the molten blend of stone and metal that flows from volcanic vents. You can imagine them pouring this molten lava into pre-made molds. In effect, the volcanic craters would both supply the raw material and greatly simplify the heating and smelting processes that demand so much energy in Earth-based metallurgy. One can even envision a scenario where Iceheim's metallurgy achieves an extraordinary degree of precision, with metallic tools being used to keep records. The single invention that might come to symbolize the triumph of their technology, much like the wheel did on our world, could be the pipe. If heat were required for any purpose, it could be transported directly to the necessary location through a pipe linked to a hydrothermal vent. If space needed to be cleared for new habitats, they could simply melt the ice walls by directing hot water through a pipe, rather than breaking and grinding the hard material as we do to build tunnels on Earth. Now, how might the inhabitants of Iceheim communicate with one another? In Earth's oceans, whales and dolphins employ sound waves that share many remarkable similarities with human language. It is therefore quite reasonable to assume that life evolving in the warm water tunnels around Iceheim's thermal vents could develop a similar reliance on sound for communication, and perhaps even use sonar for navigation. We also know that certain species of eels use electricity to interact with their environment, so electromagnetic signals could represent another avenue for communication. During the early stages of life's emergence on Iceheim, organisms that could respond most swiftly and accurately to the faintest changes in thermal radiation from predators would have possessed a significant evolutionary advantage. In a world dominated by thermal energy around a crater, interpreting heat signatures could also function as a primary method for communication and navigation. This evolutionary path is very similar to the development of the eye in Earth's organisms, a visual organ designed to gather visible light. The reality perceived by Iceheim's inhabitants would be a strange and complex mosaic of thermal markers, and it is this unique sensory world that could have provided the initial spark for the dawn of science on their planet. Here on Earth, the most ancient civilizations already held vast knowledge about the movements of the sun, moon, and planets against the backdrop of a star-filled night sky. At first, these observations served entirely practical needs. They were used to determine the right times for planting and harvesting, and possibly to follow the seasonal migrations of animals that provided people with sustenance and clothing. Later, these celestial observations became indispensable for navigation to the first travelers. The study of how planets moved in relation to the fixed stars, spurred the ancient Greeks and other cultures to formulate their initial concepts of the cosmos. Gaining an understanding of Earth's position within the vastness of the universe became a major catalyst for the advancement of most human civilizations. The first intelligent beings on Iceheim would be denied any view of the night sky. But you might ask what they would see if they did look up. Their immediate view would, of course, be the icy ceiling high above them. However, if their eyes evolved to be sensitive enough to perceive the most minuscule fluctuations in thermal radiation, they might soon discover evidence of a universe existing beyond that ceiling. If their planet has seasons, just as Earth does, the shifting position of their sun in the sky would cause thermal waves to pass through the ice differently at various times of the year. It is entirely possible that the inhabitants of Iceheim could perceive these thermal waves. They might even try to calculate the patterns of their heat source's transit across their frozen sky. This endeavor could form the foundation of their own unique cosmology, born not from light, but from the subtle language of heat. Should their world be warmed by additional heat sources, such as nearby giant planets or moons, the resulting thermal patterns would become incredibly convoluted, perhaps sparking complex theories about the cosmos. You can picture intrepid explorers from Iceheim setting out from their home crater into the frozen wastes, mirroring the ocean voyages of Europe's Age of Discovery. The essential technology for such an expedition, a simple double-walled pipe, would be relatively easy to produce. In the same way European mariners found a new world, these researchers would progressively map out new thermal craters and the life they support, possibly even navigating by the heat signatures in their icy sky. Over time, they could establish a planet-wide system of tunnels linking these thermal oases, analogous to how airline routes connect cities across Earth. If the people of Iceheim possessed a deep scientific curiosity, you could imagine them mounting an expedition to ascend through the ice shield, much like humanity's first pioneers of the atmosphere and space. Captivated by the intricate heat patterns above, they would finally orient their pipes upward instead of outward, leading to the staggering realization that their world possesses a ceiling. This discovery, however, might only fuel their desire to explore more. Their journey could lead them to find outer space itself, prompting them to question what exists beyond their icy shell. It is plausible that they would ultimately achieve space travel and set out to resolve that timeless question: does life exist elsewhere in the cosmos? Imagine you are at the helm of a submarine, gliding just over the seafloor where a sunken mountain range looms in the distance. Beneath you, a hydrothermal vent expels what looks like black smoke, and surrounding this crater are thick colonies of organisms that seem plant-like, nourished by the rich chemical brew emerging from the planet's core. You spot a school of fish to your left, their buoyancy controlled by gas-filled bladders. As you observe more carefully, you see structures that look like homes near the vent, and objects resembling balloons drifting above them. Yet for all this strangeness, one thing grabs your focus. You guide your vessel upward until its prow makes contact with a solid sheet of ice. You have found this world's upper limit. One of the most significant shocks during our initial exploration of the outer solar system was delivered by Europa, a moon of Jupiter. An astonishing find was made by the Galileo space probe, which was sent off in 1989 and arrived at Jupiter in 1995. The mission's scientific team, using data I will elaborate on shortly, determined that a genuine subsurface ocean of liquid water exists beneath Europa's frozen exterior. This comparatively small moon holds a greater volume of water than all of Earth's oceans put together. In contrast to the hypothetical planet Iceheim, which I envisioned with isolated pockets of liquid water around vents on an otherwise frozen world, Europa is completely encased in a massive ocean beneath a relatively thin ice crust. You can hardly exaggerate the profound impact this revelation had on the scientific community. Before this, researchers were convinced that Earth's oceans were the only location in the solar system with substantial water reserves. During the 1980s, one of this book's authors, James Trefil, even identified the scarcity of water as the primary barrier to human colonization of space. With its surface temperature of -223 degrees Celsius, Europa was among the least likely candidates for finding liquid water. But the Galileo probe proved that's exactly where it was. A brief examination of Europa's surface is enough to show how distinct it is from other moons. For one, it has remarkably few impact craters. Given that Europa should have been bombarded by meteorites over its lifetime, the scarcity of craters points to a mechanism that must be smoothing or resurfacing the moon. While I'll delve into that process later, it suggests Europa's current surface is younger than 50 million years, a blink of an eye in cosmic terms. Furthermore, the ice is streaked with countless cracks containing some unknown dark material that seems to well up from below, indicating the surface is composed of separate, shifting tectonic plates. Initial proof of a subsurface ocean was provided by magnetic readings from the Galileo probe. While sweeping past Europa, the spacecraft registered a magnetic field enveloping the moon, for which the best explanation was a massive, salty ocean flowing under its thin ice shell. Then, in 2016, this theory received dramatic validation when the Hubble Space Telescope witnessed enormous geysers of water vapor shooting up to 200 kilometers high from below Europa's surface. The collective body of research, therefore, points to an undeniable conclusion. Under an ice sheet several kilometers thick, Europa hosts a global subsurface ocean of liquid water, with a depth ranging from 80 to 200 kilometers. The ice crust's thickness is not uniform, and in certain regions it may be as thin as just a few hundred meters. The immediate question raised by Europa's subsurface ocean is what energy source maintains its liquid state. In contrast to Iceheim, Europa is not massive enough to generate substantial heat from either the cooling of its primordial core or the decay of radioactive materials. For these reasons, we believe it is geologically inert, much like our own moon. Yet another power source is available within Jupiter's system of moons. This phenomenon is directly tied to the immense gravitational pull of Jupiter and its other major moons, Io, Ganymede, and Callisto. As Europa travels through its roughly 85-hour orbit, its distance from Jupiter and these three large moons constantly fluctuates. This orbital dynamic causes the gravitational forces exerted on Europa to persistently change in both intensity and direction, resulting in a continuous process of bending, twisting, and compressing the moon's structure, which in turn generates heat. You can demonstrate this principle for yourself by rapidly flexing a metal strip back and forth, and then feeling the warmth at the bend. This mechanism, termed tidal heating, is what can maintain Europa's subsurface ocean in a liquid state for billions of years. A name derived from the way variable gravitational fields produce tides on celestial bodies. Following the confirmation of Europa's hidden ocean, scientists discovered similar liquid layers on Ganymede and Callisto, as well as on Saturn's moons Titan and Enceladus. The Cassini spacecraft, while orbiting Saturn, even managed to fly directly through a geyser erupting from beneath the icy crust of Enceladus, solidifying these oceans as prime locations in the hunt for extraterrestrial life. This search for life also clarifies why the Galileo probe was intentionally sent into Jupiter's atmosphere in 2003, and why the Cassini mission concluded with a similar plunge into Saturn in 2017. Both spacecraft were purposefully destroyed to prevent any remote chance of them accidentally crashing onto one of these potentially life-bearing moons and contaminating them with microbes from Earth. Before we journey beyond our solar system, it's worth remembering the data from the New Horizons probe, which revealed that Pluto also possesses a subsurface ocean of liquid water, and that its moon Charon likely had one in the distant past. The case of Pluto is particularly puzzling, however, because it lacks any source of tidal heating from nearby celestial bodies. Therefore, the origin of the heat necessary to keep its ocean from freezing over remains an unsolved mystery. There are several plausible scenarios for how a world with a subsurface ocean covering a rocky or metallic core might come into being. A large planet such as Iceheim could form with a solid ice shell over a rocky core, where the leftover heat from its formation, or significant thermal energy from core radioactivity, would be enough to melt the ice and form an ocean. Alternatively, the heat required to maintain a liquid ocean around the core could be supplied by an external mechanism like tidal heating, as was the case for Europa and other large moons in our solar system. In such instances, the flow of heat that sustains the subsurface ocean generates a growing layer of water that spreads from the bottom up. One could also envision a world where oceans initially existed on the surface, but were later subjected to extreme cooling, causing the outer layer to freeze solid, while the water beneath remained liquid. The periods in our own planet's history, known as Snowball Earth, offer compelling support for this latter scenario, demonstrating that there were times when Earth itself effectively became a world with a subsurface ocean. In these situations, the planetary structure is formed from the top down as an ice layer develops over a pre-existing liquid ocean. The Snowball Earth events also confirm that planets can shift between different categories of water worlds multiple times, further broadening the possibilities for where life might exist. Furthermore, you and I must be ready for the likelihood that the conditions for life's emergence could be drastically different on a planet's moon, influenced by tidal heating, compared to a planet on an independent orbit, where such forces are absent. This brings us to one of those fundamental questions that expose the limits of our celestial knowledge, as we do not yet grasp the intricate details of heat flow within planets and moons that have subsurface oceans. While scientists generally accept the hypothesis that heat is transported upward through convection in the water, it remains unknown if convection within the inner rocky mantle and metallic core operates under the same principles as it does on Earth. Some theorists propose that, even on a relatively small body like Europa, convection could occur in the mantle, meaning its ocean might host underwater thermal craters similar to those we discussed previously. For the remainder of our discussion, I will proceed with the theoretical assumption that this is indeed true, and we will focus exclusively on worlds with subsurface oceans that possess these underwater hydrothermal vents. Let's now delve into how life might evolve in such a setting. And in honor of the Galileo space probe's discoveries, we will name our hypothetical world New Europa. Now for a brief linguistic aside. You might recall that in 2006, during a meeting of the International Astronomical Union, a small faction of astronomers managed to pass one of the most questionable decisions in scientific history, downgrading Pluto to the status of a dwarf planet. The debate required the initiators to loosely redefine the very meaning of a planet, a full discussion of which is detailed in our book Exoplanets. Many planetary scientists have since disregarded this ruling entirely, and in this book, I will also use the conventional terms planet and moon or satellite to help you follow the reasoning more easily. Nevertheless, I feel it's important to remind you of a growing trend in the field. Nowadays, planetary scientists frequently refer to any object as a planet, including moons, provided it is massive enough to be spherical, but not so large as to become a star. I understand that calling our own moon a planet might seem strange, at least initially. However, I am hopeful that, over time, more astronomers will come to embrace this more inclusive definition, as it more accurately reflects the physical nature of these celestial bodies. As we have stated repeatedly, the most compelling scenario for life in water worlds emerges when a planet's core is substantial enough to drive tectonic activity. On the solid crust of such a world, thermal craters begin to form. It's a widely held belief among scientists that life on our own planet originated in analogous hydrothermal vents deep in the ocean, where conditions provided both the energy and the raw materials necessary for life to begin. For our discussion, let's imagine a planet with these thermal craters on its crust, all situated beneath a global ocean that is itself trapped under a thick sheet of ice. To make things simpler, we'll refer to this world as New Europa. As we previously saw with the planet Iceheim, any organism that can navigate through hydrothermal channels to reach resource-rich areas would possess a significant evolutionary edge. This same principle would apply on New Europa, but its inhabitants would have an extra option not available on Iceheim. While thick ice walls on Iceheim isolate craters from one another, on New Europa, living beings could colonize new vents with ease by swimming a short distance in any direction. Consequently, you can envision these life forms migrating between geothermal heat sources in much the same way that animals on Earth travel from one island to another across the sea. The environmental factors surrounding these sources would naturally differ greatly, leading natural selection to produce a wide variety of species around each vent, just as has happened on Earth. For instance, different hydrothermal vents could expel materials with varying chemical makeups or operate at different water temperatures, forcing life to adapt and diversify. To illustrate this point, you might consider the differences between tigers and polar bears. In terms of how energy is distributed, New Europa would be very similar to Iceheim. Heat and chemical energy would ascend through hydrothermal vents into underwater craters, but the light from its parent star would be almost entirely blocked by the overlying ice layer. You can picture life forms emerging near these vents and slowly journeying upward, following the flow of energy and nutrients toward the bottom of the ice shield, which for them would mark the very boundary of their universe. Just as on Iceheim, the organisms that could somehow penetrate the ice and access the energy from the parent star would gain the ultimate advantage. We can imagine a few scenarios for how this might happen. For example, water carrying microbes could seep to the surface through cracks and fissures in the ice. Furthermore, we know from worlds with subsurface oceans in our own solar system, like Jupiter's moon Europa, which we'll call Old Europa to avoid confusion, that geysers of water sometimes erupt through the ice, providing another pathway to breach the shield. A final method involves large meteorite impacts, which could fracture the ice and cause water from the planet's interior to flood the surface. As this water freezes, it forms a fresh layer of ice, a process astronomers call surface renewal. This explains why Old Europa has so few impact craters. Through any of these mechanisms, living organisms could potentially be transported to the surface and into the light of their star, where they would need to evolve a process like photosynthesis to utilize that energy. However, all of these arguments bring up another puzzle: It would appear that on worlds with subsurface oceans, life could find its way to the surface with relative ease. Yet we have found no evidence of it on any such worlds in our solar system. It is possible that the presence of tidal heating is a critical factor here, meaning the question of whether we are looking at an independent planet or a moon could be decisive. Perhaps on worlds like New Europa, all routes to the surface are obstructed for reasons we do not yet understand. It might be that these worlds are simply too distant from the sun for surface life to be sustainable. In the last chapter, we talked about how large leaves could make up for dim sunlight, but there could be an evolutionary choke point between deep ocean microbes and large-leafed plants that organisms struggle to overcome. Alternatively, tidal heating could introduce some unknown variable that actively prevents movement to the surface. Or, it could just be that life never emerged on these specific bodies in the solar system in the first place. You should also consider another possibility. Jupiter relentlessly showers old Europa with high-energy particles. This radiation is strong enough to obliterate any life on its exposed surface, though it only penetrates a few inches into the ice. This suggests that if surface life does exist on Europa, it might be found not on the very top of the ice shield, but several inches or even tens of inches deep within it, where our current probes and telescopes cannot detect it. There is one more element that might account for the lack of life on the surfaces of these moons. It has to do with what we observe in the food webs of Earth's oceans, excluding the unique ecosystems around hydrothermal vents. The entire intricate network of food chains in our deep seas is dependent on sunlight. At the base of these chains are microscopic organisms such as phytoplankton, which use photosynthesis to convert sunlight into energy. This process is confined to a layer of water, known as the photic zone, that sunlight can only reach down to about 800 meters. Every other creature in the marine ecosystem ultimately relies on the energy captured by this photosynthetic plankton. On New Europa, the ice shield would entirely prevent a photic zone from forming, as the light from the parent star would be unable to pass through the thick ice to the water below. It's worth noting that both NASA and the European Space Agency are currently planning missions to collect and analyze the dark material that emerges from the cracks on Europa's surface, which could hold the answers we seek. Confirming this, however, would involve landing a descent craft equipped with sophisticated instruments for chemical analysis, much like the rovers we deploy on Mars. After touching down on Europa, it is highly likely that the first step would be to drill through the ice shell to obtain samples of the water underneath. If the probe were to identify living organisms, we could then begin to trace the evolutionary path that brought them into existence. Should it find nothing, this would suggest that life has a more difficult time developing in worlds with tidally heated subsurface oceans than we had previously imagined. Ultimately, the question of why life isn't present on the surfaces of such worlds must be answered by collecting and analyzing fresh data, not by relying on purely theoretical arguments. In the end, information from missions sent to Europa might illuminate the potential for life on a planet like New Europa, but it is equally possible that it could leave us without any definitive conclusions. As is the case with most exoplanets, you can see we are confronted with numerous unanswered questions, a topic we will explore more deeply in Chapter 17, when we discuss intelligent life and technological advancement. We are aware that the earliest multicellular life on our own planet flourished near underwater hydrothermal vents, so it seems reasonable to postulate that multicellular organisms on New Europa might have evolved through a similar process. Once more, I must stress that we simply do not have the data to make any firm conclusions about intelligent life emerging in such an environment. But if you assume for a moment that intelligence and technology did arise there, we can speculate on the nature of a civilization that developed in the depths of a subterranean ocean. Similar to the conditions on Iceheim, the rocks on the ocean floor, combined with materials from volcanic and hydrothermal craters, could offer an ample supply of metals and chemicals to fuel technological progress. Just as the wheel serves as a symbol for Earth's technology and the pipe for Iceheim's, the technological emblem of New Europa would surely be the buoyancy sphere, which would function as the most vital method of transport in that world. A sphere filled with gas, or perhaps a liquid less dense than the water around it, would permit the inhabitants of New Europa to ascend from their planet's solid surface and thoroughly investigate their environment. You can envision their first explorations being mostly horizontal, moving parallel to the ocean bed. The New Europeans would likely chart this floor, surveying it from above, in a manner reminiscent of how European sailors mapped the various corners of Earth during the Age of Discovery. In time, however, they would inevitably turn their gaze upward and become aware of the vast expanse of the subsurface ocean stretching above them. To ascend, all they would need to do is inflate their buoyancy bladders with the lightest liquid available. And there, they would meet the ice dome. What might occur if, at the very beginning of its space age, humanity had run into a physical barrier that blocked our path further and higher? The ancient Greeks imagined that just such a barrier encased the Earth, a solid crystalline sphere to which the moon was attached. They accounted for the moon's nightly journey across the sky by the rotation of this sphere. Would the New Europeans devise a cosmology around a comparable theory, content to have reached the limit of their universe? Or would they be bold enough to attempt tunneling through the ice to discover what lies beyond? It's entirely plausible that events on New Europa would, at some point, parallel the scientific and technological journey we have experienced on Earth. The primary distinction would be that Earth's scientists have concentrated on moving inward, deep into our planet, to comprehend its structure. In contrast, scientists on New Europa would focus their efforts upward, toward the ice canopy that covers their world. The rise of seismology in the 20th century enabled us to map the Earth's internal structure. Likewise, New Europa's scientists could create methods using sound waves to probe the ice layer, eventually learning that it has a finite thickness and does not stretch on forever. Scientists on Earth have also pursued deep drilling, with the current record held by the Kola superdeep borehole in Russia, near Murmansk, which extends more than 12 kilometers into the Earth. If the New Europeans had access to equivalent technology, they could probably reach the surface of their ice shield by drilling a vertical shaft, assuming the ice is of a comparable thickness to that of Jupiter's moon Europa. The motivation for such an undertaking, however, would likely be more than simple curiosity. Breaking through to the ice surface could yield enormous technical and economic advantages by allowing the New Europeans to capture and utilize energy from their star's radiation. Just as we harness geothermal energy for electricity or heating, they could position solar panels on the ice's surface. You could even picture a competitive race to the surface among civilizations originating from different hydrothermal vents, much like the 20th century space race on our own planet. One can imagine vast energy installations on the ice, surrounded by fields of solar panels, and linked by long cables to the ocean floor below. There is a clear parallel between the New Europeans leveraging the ice surface for their needs and humanity's use of near-Earth space. Currently, humanity relies on satellites mostly for communication and navigation, although there is already discussion about constructing a massive solar power station in Earth's orbit. The new Europeans, while maintaining their energy facilities on the outer ice surface, would require protection from the vacuum of space or their planet's atmosphere, in the same way humans on the International Space Station need shielding from the hostile conditions outside. For this very reason, much of our own space exploration is carried out by unmanned, automated probes. The new Europeans might adopt a similar strategy, sending machines and robots to their world's surface while they remain in the safety and comfort of their underwater homes. Or, perhaps, like humans, they would be driven to venture toward the newly discovered stars and explore them firsthand. To push this research forward, they would need to conquer a multitude of challenges. Simply penetrating the outer ice shell would represent a monumental undertaking. Constructing facilities on the planet's surface, analogous to our spaceports, would demand years of dedicated work and an immense concentration of resources. In terms of sheer ambition and resource allocation, such a project would be comparable to humanity establishing a permanent settlement on the moon, an endeavor for which we already have blueprints. There is no reason to think the new Europeans would possess any less of a drive for such grand-scale achievements. It is also compelling to imagine how the new Europeans might engage with space travel and the colonization of other planets. For generations, humans have dreamt of discovering a second Earth, a rocky world with liquid water on its surface, orbiting a distant star that we could settle as a new home for our species. This is the kind of world we define in Chapter 9 as an Earth-like planet. And while we've found dozens of candidates, Earth remains the only one in our solar system. In contrast, the new Europeans would probably seek out ice-covered worlds with oceans hidden beneath, and our solar system alone offers at least 5 such bodies: Europa, Ganymede, Callisto, Titan, and Enceladus. Consequently, the inhabitants of New Europa would enjoy a significantly higher probability of success in their colonization efforts, allowing them to spread throughout the galaxy much more quickly than humans ever could. Imagine yourself adrift in a small boat, with an unbroken expanse of water stretching to every horizon. Since you've been to this planet before, you're aware that this view remains constant no matter which direction you travel. White clouds drift across the sky above, appearing peaceful, but you recall their capacity to swiftly gather into storm fronts. Great birds, much like albatrosses, soar overhead, having evolved to incubate their eggs while bobbing on the water's surface. Below your vessel's keel, you can spot schools of fish, while somewhere in the abyssal darkness, massive aquatic predators hunt them. Even deeper, 150 kilometers down, unimaginable pressures force water molecules into exotic forms of ice. You have arrived on Neptunia. We are continuing our survey of worlds where a rocky mantle and a metallic core are enveloped in water. This time, we are exploring an extreme example. A planet whose surface is completely submerged beneath a single continuous ocean, without any land at all. You shouldn't find the existence of such worlds surprising, as humanity is already aware of several planets that fit this description. One such planet is Gliese 1214, which we will explore in depth in Chapter 14. Situated 40 light-years from Earth, it has been nicknamed a water world by astronomers, a nod to the 1996 science fiction movie. The ocean that entirely blankets its surface could be as deep as 150 kilometers. Here, then, is another setting where the kind of life we imagine could arise. Let's give it a more evocative name than our astronomical colleagues might. We'll call it Neptunia, in honor of the Greek god of the seas. The first crucial detail about Neptunia is that its orbit must be within its star's habitable zone. This is the specific region where stellar radiation is sufficient to keep the planet's vast ocean in a liquid state. If an ice crust covered Neptunia's ocean, it would be a world very similar to New Europa from the last chapter. And if that ocean were frozen solid to its core, Neptunia would instead resemble Iceheim from Chapter 6. As I've stated many times, water worlds come in many varieties, and one type can always evolve into another. To grasp how a world like Neptunia might come into being, let's review the formation of Earth's own oceans. During our planet's molten infancy, the least dense materials migrated from the core to the surface, eventually forming the continents we know today. This material, however, only covered about a quarter of Earth's total surface, leaving immense depressions between the land masses. You can think of these basins as gigantic bathtubs waiting to be filled. The water that eventually filled them originated from three sources: volcanic outgassing from Earth's interior, delivery by asteroids and comets that impacted the planet, and capture from passing comets. Scientists continue to debate the primary source and the exact contribution of each. The final outcome, however, is that our terrestrial bathtubs were filled, but the water level did not overflow their brims. Yet, this overflow is not an impossible scenario. Had Earth accumulated approximately 5 times more water than it did, every continent, including the highest mountain ranges like Mount Everest, would be completely submerged. Earth would have transformed into a planet just like Neptunia. The ultimate quantity of liquid water that collects on a planet's surface is determined by a host of factors, including the amount of water present in the initial nebula, the portion of that water captured by the planetary embryo during its formation, the planet's mass and resulting gravitational force, and, naturally, its surface temperature. Considering what we discussed in Chapter 1 regarding the sheer number and diversity of planets in the galaxy, it is safe to assume that worlds like Neptunia are quite prevalent. Here, I will make a short digression to mention that early in the solar system's history, the orbits of the outer planets underwent a significant rearrangement. This event destabilized the paths of countless comets and asteroids, sending a barrage of them careening toward Earth. We aren't certain if such orbital reorganizations are a standard part of planetary system formation, but we do know they sometimes happen. In our system, this bombardment from comets and asteroids never ceased entirely. It has merely tapered off over time. Even today, about 40 tons of cosmic material collides with our planet daily, burning up in the atmosphere and settling on the surface as a fine dust, steadily increasing Earth's mass. Considering the conditions for life, the flow of energy on Neptunia would not be fundamentally different from the systems we have already analyzed on Iceheim and New Europa. On the world of Neptunia, sunlight bathes the ocean's surface, while the planet's molten core provides warmth from below, venting heat through hydrothermal fissures on the seabed, alongside energy from chemical reactions. What sets Neptunia apart is that it's the first world we've considered where life could potentially emerge in 2 distinct environments. Much like on Earth, at the surface, where liquid water is present, and in the deep ocean, clustered around those geothermal vents. As we covered in Chapter 4, the Miller-Urey experiment revealed how basic chemical processes in Earth's early atmosphere could have generated the fundamental molecules necessary for life. This research supports the primordial soup hypothesis, which suggests these building blocks rained down, transforming the ancient ocean into a dense, organic-rich broth. From that point, once the first cell appeared, Darwinian natural selection would have driven evolution forward, a process that doesn't depend on the existence of continents and could therefore easily occur on Neptunia. However, one major hypothesis for the origin of life on Earth would be completely invalid on Neptunia. The warm little pond, or, to use its scientific name, the tidal pool theory. The logic here is inescapable, as tidal pools can only form on land, a feature that this water world entirely lacks. This makes it the sole earthly origin theory that simply cannot be applied to this particular planet. Assuming life on Neptunia did arise from a primordial soup akin to Earth's, its evolution would likely follow a comparable trajectory to that of our own oceans. A sunlit photic zone, extending several hundred meters down, would develop, fostering a food chain founded on a thick layer of phytoplankton. Over time, this would give rise to more sophisticated organisms, potentially culminating in creatures resembling predatory fish. Yet, this ecosystem would be devoid of shallow water species like algae or oysters, and it would also never produce air-breathing marine animals like whales, whose ancestors first evolved on land before returning to the water. Down in the abyssal depths, the conditions surrounding Neptunia's hydrothermal vents would probably be very similar to Earth's. Since the ocean's extreme depth isn't a critical factor when analyzing these deep-sea biomes, we can infer that evolution at the seafloor would unfold in a familiar manner. Consequently, life at both the upper and lower boundaries of Neptunia's ocean would likely mirror terrestrial forms. It is in the vast middle ground, between the surface and the abyss, where a new and powerful force would dictate a very different evolutionary story. Tremendous pressure. Whether you realize it or not, your entire existence is spent at the bottom of an immense ocean of gas that we refer to as the atmosphere. To grasp this, trace a small square on your palm, roughly an inch on each side, and then picture a column extending from that square all the way to the edge of space. If you are standing at sea level, the air contained within that imaginary tube weighs about 6.5 kilograms, a force that is pressing down on every square inch of your hand at this very moment. Your body, in turn, pushes back with an identical force of 6.5 kilograms per square inch. Because you have lived with this equilibrium since birth, you are normally completely unaware of it. You only perceive this pressure when you enter an environment where it differs substantially, such as at high altitudes where the air column is shorter and the pressure drops, requiring pilots to wear pressurized suits. Descending to the ocean floor has the opposite effect, adding the weight of all the water above and increasing pressure so much that divers need reinforced equipment to survive. Pressure is fundamentally the amount of force applied over a unit of area. The Earth's atmosphere at sea level, for instance, exerts a pressure equivalent to the weight of 1 kilogram on every square centimeter of surface. This value is standardized as 1 atmosphere, or ATM. Scientists often use a comparable unit called the bar, while weather reports frequently cite millimeters of mercury, a historical measurement based on the height of a mercury column, 76 centimeters, needed to balance the weight of the atmosphere. The official metric unit of pressure is the Pascal, named after the French scientist Blaise Pascal, who was the first to explain the principles behind the barometer. 1 atmosphere is roughly equal to 100,000 pascals. You've likely encountered pressure measurements yourself, either at a doctor's appointment or when adding air to your car's tires. A blood pressure reading of 120, for example, indicates that your arterial pressure is 120 millimeters of mercury above the standard atmospheric pressure of 760. Likewise, the gauge for your tires is calibrated in PSI, which stands for pounds per square inch. It's quite peculiar how various scientific and practical disciplines use completely different units for pressure, a practice that continues despite some official objections. For instance, you'll find that medical professionals and weather forecasters still rely on millimeters of mercury, while engineers often work with PSI, and scientists prefer bars. This stubbornness appears to stem from a simple reluctance to abandon familiar, long-established systems of measurement. What other reason could there be for the fact that if you walk into an American hardware store to buy nails, you'll find their sizes listed in pennies, marked with the letter D? This unit is a direct legacy from the Roman Empire, where D stood for denarius, an ancient silver coin. This resistance to change is also why the United States is the last remaining developed nation that hasn't adopted the metric system. However, I have to confess, along with my co-author, that we see a certain logic in this hesitation, as a full conversion to the metric system would likely create more problems than it would solve. Speaking of immense scales, let's return to the topic of pressure, which, as we've discussed, builds as you go deeper into the ocean. The most extreme depth on our planet is the Mariana Trench in the Pacific Ocean, reaching down nearly 11 kilometers, or, more precisely, 10 kilometers 1,994 meters. Down there, the pressure from the water reaches 1,086 bars, which is over 1,000 times greater than the standard atmospheric pressure you experience at sea level. To give you a tangible sense of this force, try to picture an elephant balancing on every single square inch of your body. Then, just to be sure, imagine another elephant added for every 4 inches of that surface area, which is about 25 centimeters. Now, if we imagine that Neptunia's core is comparable in size to Earth's, and that its ocean plunges to a depth of 160 kilometers, the pressure at the ocean floor would be approximately 16 times higher than in the Mariana Trench. This would be equivalent to having 20 elephants standing on each square inch of you. Remarkably, scientists can readily generate these colossal pressures in a lab with an instrument known as a diamond anvil cell. This apparatus works by positioning the material being tested between a pair of diamonds. One of the diamonds is fashioned with a small hollow for the sample, while the other is shaped with a point designed to fit perfectly into that depression. Because pressure is a function of force distributed over an area, and the point of contact here is nearly microscopic, it's possible to generate immense pressure using a surprisingly modest amount of force. A diamond anvil cell can actually produce pressures that are far greater than anything we would expect to find even on Neptunia. Interestingly, there's a certain Wild West quality to high-pressure physics. Researchers in this area will tell you that when one of their diamonds finally gives way and shatters, it makes a noise just like a pistol shot. Under extreme pressure, materials begin to act in very peculiar ways, as their fundamental properties can be completely transformed, because the very configuration of their atoms and electrons is altered. Take oxygen, for example. A gas that is normally colorless and without taste will first turn blue as pressure mounts, then solidify into a ruby-red crystal, and ultimately become a reflective metal. Other substances undergo comparable transformations, but here on Earth, these changes can only be witnessed inside a laboratory, since the pressure at the bottom of the Mariana Trench is nowhere near high enough. To truly grasp what you would encounter on a descent into Neptunia's ocean, we first need to explore the idea of a phase transition. Typically, we think of a substance like water as existing in one of 3 states or phases: a gas, a liquid, or a solid in the form of ice. The processes that shift a substance between these states, like boiling or freezing, are known as phase transitions. For our purposes, the shift from liquid to solid is the most important, so let's look at what's occurring on a molecular scale when a substance freezes. In a liquid state, molecules can slide past one another freely while still staying in contact, much like a small pouch of marbles that you can feel rolling around. By contrast, molecules in a solid are rigidly bound together in fixed structures, almost like pieces from a Lego set. To convert a liquid into a solid, energy has to be extracted from the system, which in turn restricts the molecule's freedom to move. This is precisely the principle at work when you drop an ice cube into your beverage. The drink's heat energy is expended to melt the ice, causing its state to change and thereby lowering the overall temperature of the liquid in your glass. It often comes as a shock to people when they find out that ordinary water, or H2O, is actually one of the most enigmatic materials known to science. Researchers have discovered that by manipulating temperature and pressure, water can be forced into at least 17 distinct phases of ice. Each of these phases is defined by the unique crystalline arrangement of its hydrogen and oxygen atoms. Scientists usually label these different forms with Roman numerals, giving us names like Ice X or Ice 11, which we will touch on later. It's crucial to point out, however, that none of these real-world ice phases are related to the imaginary Ice 9 from Kurt Vonnegut's novel Cat's Cradle. The kind of ice you encounter every day, the stuff you might find on a sidewalk during a cold snap in January, is known as Ice IH. Its water molecules organize themselves into a hexagonal lattice, which is what the H in its name signifies. On Earth, it's impossible for natural conditions to generate the pressure needed to change Ice IH into another form. Yet at very cold temperatures below -22 degrees Celsius, a different structure called Ice 11 can emerge, where the hexagonal patterns are more perfectly aligned than in Ice IH. Things get much more intricate when we factor in the kinds of pressures anticipated at the bottom of Neptunia's ocean. With a depth of 160 kilometers, the pressure at the seafloor would climb to around 16,000 atmospheres. That level of force is enough to transform liquid water at ordinary temperatures into a phase known as Ice 6. In Ice 6, the molecules create a tetragonal or rectangular lattice. You can visualize this by imagining a cube being stretched until its square faces become rectangles. Consequently, this immense pressure would create a solid layer of Ice 6 directly on top of Neptunia's rocky mantle, with a vast liquid ocean existing above it. This implies that the deep ocean environment on Neptunia would closely mirror that of Iceheim, featuring water bubbles and tunnels over thermal vents where life could flourish beneath an ice sheet. This entire discussion highlights a critical characteristic of water. Increasing the pressure can force it into some form of ice, no matter the temperature. It is this principle that makes the boundary between the core and mantle on water worlds so incredibly intriguing. For example, you might theorize that heat from oceanic thermal vents reaching the planet's rocky crust could melt the ice layers resting directly upon it. However, if the pressure at the bottom of Neptunia's ocean were even marginally greater, perhaps because the planet's solid core is substantially larger than Earth's, or the ocean is much deeper than our 160-kilometer assumption, we would be forced to discard that initial hypothesis. Under such immense pressures, a substance known as Ice X would start to materialize. The cubic crystals of Ice X can only exist in extremely high-pressure conditions, which are unattainable on Earth outside of a laboratory. but are entirely conceivable on exoplanets. From our perspective, the most bizarre quality of Ice X is that it cannot be melted by raising the temperature. Once pressure converts water molecules into this state, no amount of heat from magma welling up from the planet's interior can break them apart. A water world with a layer of Ice X overlaying its crust would be an exceptionally volatile place. Magma flowing onto the rocky seabed would be pinned down by an unyielding layer of non-melting ice. This would establish a tense standoff between the upward force of the magma and the structural integrity of the ice shield, with the outcome hinging on specific factors like the thickness of that ice layer. For instance, a comparatively thin sheet of Ice X could perpetually buckle and fracture, much like Earth's solid outer crust, which breaks into tectonic plates as magma rises through mantle convection. In this case, the Ice X boundary would function analogously to our own planet's crust. Conversely, if this layer were sufficiently thick, the convective heat reaching it would steadily accumulate until the magma finally burst through in a cataclysmic explosion or eruption. This is the very scenario we believe unfolds on Venus. Its crust is thin, allowing heat to build up beneath it until it is catastrophically released, shattering the crust into fragments that then sink into the underlying magma. This process is thought to recur on Venus approximately every 500 million years. The potential for life to arise on such a surface hinges on how long a stable layer of Ice X can persist before being obliterated by the accumulating heat. If the lifespan of this ice layer extends beyond hundreds of millions of years, the formation of complex chemical compounds becomes plausible. But if the layer is destroyed frequently, the conditions would likely be far too unstable for life to ever get a foothold. Consequently, we must define limits for Neptunia's core size and ocean depth, beyond which the properties of Ice X would render life impossible, confining any potential biology to the ocean's surface. Let's refer to this threshold as the Ice X limit. When considering intelligent life and technological advancement, Neptunia presents a world where life could potentially arise both on the surface and at the ocean floor. I propose we examine the probable developmental paths for a technological civilization in each of these distinct scenarios. If the pressure at the bottom of the ocean is great enough, a layer of Ice 6 will form. Otherwise, liquid water will stretch from the crust all the way to the top. If an ice layer were present at the seafloor, the situation would be reminiscent of our discussion of Iceheim in Chapter 6. You may recall that the symbol of technological progress in that world was the pipe, a device for transferring heat from a hydrothermal vent to other areas. The key distinction is that if Neptunians journeyed to the upper boundary of the Ice 6 layer, they would find an atmosphere of liquid water, not gas. These beings would never see the stars, unless they devised a method for reaching the ocean's surface, a feat that would demand an entirely new category of technology. However, something being entirely new does not make it impossible. For the Neptunians, a trip to the surface would seem no more outlandish than a voyage to Mars does for us today. When you contemplate hypothetical intelligent life on the surface of Neptunia's ocean, the evolution of life in Earth's oceans can offer a useful parallel. Many of the creatures in our oceans that we suspect possess intelligence, like dolphins and whales, did not originate there. The fossil record shows their evolution from fully terrestrial ancestors over tens of millions of years. In fact, the skeletons of modern whales still contain minuscule bones, which are vestigial reminders of the limbs their distant ancestors used for walking. Therefore, even though whales and dolphins inhabit the deep ocean far from any shore, they could not have emerged or evolved on a world like Neptunia, which completely lacks land masses. Another set of Earth's marine inhabitants suspected of some intelligence includes octopuses and lobsters. These animals, however, live on the seafloor of shallow seas, generally in continental shelf zones. Since Neptunia is devoid of such shallow regions, we suspect that Earth-like intelligent species could not have developed on the surface of a water world. There is one more significant hurdle for the emergence of a technological civilization on the ocean's surface: the absence of materials for tool-making, a topic we covered in Chapter 3. Any multicellular inhabitants of Neptunia's ocean surface would be entirely without solid resources, such as the stones that our own distant ancestors utilized at the very dawn of civilization. On the ocean's surface, the only forms of solid matter you could possibly find would be drifting ice, or perhaps more permanent polar ice caps. Consequently, we are convinced that on a classic water world, enveloped by a deep global ocean and devoid of polar caps, the development of a technological civilization at the surface is improbable. This isn't because the waters of Neptunia are barren of metals. We know that Earth's own oceans contain almost every naturally occurring element from the periodic table. The crucial difference is that these substances entered our seas through continental erosion, a process absent on Neptunia, forcing any surface dwellers to rely on underwater volcanic eruptions or asteroid impacts for access to metals and other heavy elements. It is plausible, however, that Neptunians could have evolved to extract these essential elements directly from the water through filtration, maybe using oversized mouths or gills. Over time, they might accumulate enough of these materials within their bodies to form rigid structures, not unlike Earth's armored fish, which could then serve as the raw material for tool-making. We see a precedent for this in our own world with certain bacteria that process metals from water. Magnetotactic bacteria, for instance, filter iron oxides to create tiny internal magnetic chains, which help them navigate up or down in the water column toward sunlight or nutrients. If such a phenomenon could arise through evolution on Earth, there is no compelling reason to dismiss its possibility on Neptunia. Further development of these organisms could lead to the integration of silicon or metallic components into their cellular structures, which might eventually become integral to more complex, multicellular life forms. Even so, this scenario still strikes us as somewhat fanciful. While life could certainly flourish at both the surface and the bottom of Neptunia's ocean, we believe that a truly advanced civilization would most likely originate in the depths, a process we explored in the chapters on Iceheim and New Europa. Should a technological civilization arise on Neptunia, it would find a clear advantage in colonizing and settling the ocean's surface, where the light of its parent star would offer a new source of energy. I envision this expansion as being analogous to humanity's own exploration of near-Earth space. Thus, whether the seafloor is overlain with liquid water or the high-pressure ice known as Ice 6, a deep ocean civilization would probably ascend to the surface in due time, with the submarine becoming the ultimate symbol of its technological progress. Once Neptunians had breached the ocean's surface, they would likely seek to build a permanent settlement, a task no more daunting than humanity's ambition to colonize Mars. You can picture enormous structures, first assembled on the ocean floor, then made buoyant and floated to the surface, with giant tanks filled with gas captured from hydrothermal vents. Similar to future human colonists on Mars, these Neptunians would find themselves in an environment with drastically lower pressure than their bodies are accustomed to, necessitating pressurized habitats and specialized suits for any excursions outside. However, unlike the settlement of Mars, we can identify strong economic motivations for Neptunians to occupy the ocean's surface. We've already noted solar power as a potential export from a surface colony to the cities below. Another valuable export could be food, processed into organic compounds from phytoplankton harvested in the sunlit photic zone. These algae could be compressed into weighted blocks and simply dropped into the ocean to sink to the bottom. A two-tiered Neptunian civilization, coexisting on the surface and in the abyss, could give rise to fascinating scenarios. For instance, what if a surface colony grew so large that it began to demand its independence? Could a war for liberation erupt, with the surface dwellers dropping explosives into the depths and the deep-sea inhabitants retaliating with upward drifting, explosive-filled bubbles? Might you see a parallel to the Boston Tea Party, where inhabitants of the deep tear apart the algae blocks and let the pieces drift back to the top in protest? And if harmony prevailed between the depths and the surface, would the Neptunians go on to develop astronomy and space exploration? If so, might there come a day when they venture out in search of other water worlds? After all, it seems entirely possible. Mike and Jim. Jim. It feels wonderful to recline in a chair under the warm sun, hearing the soft whisper of waves as they meet the sandy shore. A light breeze rustles the green leaves, and the whole world seems to beckon you to relax and soak in the tranquility. A short distance away, a dragon makes slow, lazy circles in the sky. If it weren't for that dragon, you could easily mistake this place for Earth. We all recall the children's story of Goldilocks and the Three Bears, though in the Russian telling of the tale, the girl is, of course, named Mashenka. We tell our children and grandchildren time and again how Papa Bear's porridge was excessively hot, Mama Bear's was too cold, but the little bear's porridge was just perfect. When scientists started to theorize about Earth-like life that could only appear if a planet's oceans stayed liquid for billions of years, it became evident that the planet's temperature had to be neither too high nor too low, but precisely right. It's no wonder, then, that they designated Earth as a Goldilocks planet, the first of its kind to be discovered, but not the last. In common with all stars of its type, our Sun has been steadily increasing in brightness over the 4.5 billion years since it came into being. When the oceans on Earth first appeared around 4 billion years ago, the Sun was approximately 30% less luminous than it is now. For the oceans to avoid freezing solid, our planet had to capture and hold on to a much greater share of the solar energy that reached its surface. Over the subsequent eons, as the Sun's heat intensified, Earth's atmosphere underwent its own transformations, and the greenhouse effect started to regulate the planet's climate. You may recall that greenhouse gases function by absorbing infrared radiation that tries to leave the planet's surface, and then re-radiating it. Because a portion of this re-radiated energy is directed back downwards, the world experiences a gradual warming. Yet, despite these powerful forces, the temperature of Earth's oceans has consistently hovered just a few degrees above freezing throughout our planet's history, never becoming excessively hot or cold. To illustrate these atmospheric shifts, let's look at one of many examples. We are aware that 3.5 billion years ago, Earth's oceans were filled with colonies of cyanobacteria, which you might recognize as modern pond scum. In that era, the atmosphere was nearly devoid of free oxygen, but these cyanobacteria expelled oxygen as a waste product of photosynthesis, much like today's plants. At first, This newly produced oxygen was almost entirely consumed by chemical processes, such as the oxidation or rusting of Earth's crust. However, about 2 billion years ago, its atmospheric concentration spiked dramatically in what scientists term the Great Oxygenation Event. It's widely thought that during this period, a vast number of Earth's inhabitants, which were mostly anaerobic, were wiped out, poisoned by the very oxygen they had generated. A small fraction of life, however, successfully adapted, learning to harness oxygen for respiration, and thereby becoming the earliest ancestors of humans and all other animals with this ability. It is fascinating to note that many of the planet's most significant iron deposits, such as the Mesabi Range in Minnesota, were formed during this very period. The vast quantities of released oxygen reacted with iron dissolved in the ocean, causing the oxidation byproducts to settle on the seabed and create iron-rich layers of sediment. So, it is entirely plausible that the steel in your own car has its origins in the Great Oxygenation Event. In 1978, the astrophysicist Michael Hart, who was then a researcher at Trinity University in Texas, shared the outcomes of a computer simulation modeling Earth's atmospheric history. His model proposed that the limited heat from the young sun was amplified by a greenhouse effect driven by atmospheric ammonia and methane, which are both potent greenhouse gases like the more familiar carbon dioxide. According to Hart's simulation, as the sun's luminosity grew, the oxygen produced by living organisms started to decompose these atmospheric compounds. This action diminished the greenhouse effect, effectively balancing out the sun's increasing radiation intensity. This process ultimately led to the formation of our present-day atmosphere, in which a blend of carbon dioxide and water vapor maintains the greenhouse balance. In essence, Earth navigated an incredibly fine line between a runaway hothouse scenario and a complete deep freeze. From our standpoint, however, the most captivating aspect of Hart's work was his investigation into what might have occurred if Earth orbited at a different distance from the Sun. His model indicated that had Earth been just 1% farther away, or 5% closer, the fragile equilibrium that has kept our oceans liquid would have collapsed. Consequently, the study of our planet's atmospheric evolution led to the realization that a zone must exist around every star where surface oceans can stay liquid for billions of years. This specific orbital band is known as the circumstellar habitable zone, or more simply, the habitable zone. The idea of the habitable zone quickly became a cornerstone in scientific discussions about the potential for life on exoplanets. When considering the habitable zone and habitability, the first thing to understand is that such a zone is a feature of every star. This means that for any given star, a region exists where the energy balance would sustain a planet's surface temperature between the freezing and boiling points of water. For smaller, fainter stars, this habitable region is quite narrow and situated very near the star. Indeed, many known exoplanets in these zones orbit their stars more closely than Mercury orbits our Sun. In contrast, for large, brilliant stars, the habitable zone is much broader and located farther out. Furthermore, as we've already discussed, a star's energy output rises with age, causing its habitable zone to progressively migrate outward over time. The most critical takeaway for us is that since every star has a habitable zone, we can anticipate that some planets will end up inside these zones through sheer statistical probability. Over the last 10 to 20 years, however, scientists have come to understand that assessing the conditions on these planets involves more than a simple calculation of temperature balance. As Massachusetts Institute of Technology astrophysicist Sarah Seeger points out, there is no assurance that a planet within the habitable zone is actually a viable home for life. As the field of exoplanet research has expanded, the quest for Earth-like worlds within the habitable zone has evolved into a kind of holy grail for astronomers. Yet, we now grasp that a planet's location within this zone and its genuine habitability are two very different things. For instance, in chapters 6 and 7, we explored worlds that lie outside their stars' habitable zones and lack oceans of liquid water on their surfaces. Even on such planets, it is still conceivable that life, and perhaps even advanced civilizations, could arise. These insights have prompted scientists to take a much broader perspective on the conditions required for life to begin. The nature of the star a planet orbits is a critical factor, heavily influencing the chances of life emerging, even for worlds within the habitable zone. For example, red dwarfs, which are the most numerous stars in the Milky Way, are small, dim, and often prone to intense bursts of activity. Powerful flares and massive ejections of charged particles would create a hostile environment, severely complicating the rise of life on any planet, regardless of its location. To endure such conditions, any organisms would need to exist deep within an ocean or far beneath the ground, a scenario where the conventional definition of a habitable zone becomes largely irrelevant. Scientists are increasingly moving away from the assumption that life must originate on a planet's surface. Many researchers, for instance, now subscribe to the theory that if life exists on Mars, it will be discovered underground. Similarly, if there are living things in the subsurface oceans of worlds in the outer solar system, such as Europa and Enceladus, they would, by their very nature, be subterranean. It's even plausible that here on Earth, a greater amount of biomass resides below the surface than upon it. Therefore, the violent activity of small stars doesn't completely rule out the possibility of life, even though our current technology would most likely be incapable of detecting it. On the other hand, more massive stars offer a much more stable radiation environment, but their lifespans are considerably shorter, sometimes lasting only 30 million years. It is highly improbable that anything more sophisticated than simple microbes could evolve on a planet within such a brief window of time. Furthermore, these stars conclude their existence with a spectacular supernova explosion, an event that would utterly vaporize all surrounding planets. Due to these limitations, those who hunt for exoplanets have concentrated their efforts on finding worlds within the habitable zones of medium-sized stars very similar to our own Sun. The second major topic of discussion concerning the emergence of life is the dynamic and evolving nature of planetary atmospheres. Earth's great oxygenation event, which I described earlier, is just one illustration of the kinds of transformative processes that can occur. Of course, there are many others, and I want to explore a few that are especially significant for planets similar to our own. For smaller worlds like Mars, a process known as atmospheric dissipation plays a crucial role in their development. This occurs because the molecules in an atmosphere are in constant motion, moving faster as the temperature increases. At any given temperature, some molecules will inevitably be moving much faster than the average, while others will be moving more slowly. If one of the faster-moving molecules is traveling upward, it might achieve enough velocity to overcome the planet's gravitational pull and escape into the vastness of space. A larger planet possesses stronger gravity, making it easier to hold on to its atmosphere. For a molecule to escape Earth, it would need to reach a speed of about 11 kilometers per second. Additionally, heavier molecules are more difficult to accelerate than lighter ones, which means dissipation allows lighter gases to escape a planet far more readily. Earth, for example, has lost a substantial amount of its original hydrogen and helium, which were the lightest components of its early atmosphere. In contrast, Mars has lost even heavier gases, including oxygen and nitrogen. Another mechanism tied to this process is photodissociation, which has a particular impact on water molecules. If a planet has surface water, its atmosphere will contain water vapor. Ultraviolet radiation from the host star can break apart these water molecules in the upper atmosphere, causing the resulting hydrogen to escape into space, while the oxygen chemically combines with surface minerals to form oxides. It's hypothesized that this is how Mars lost its ancient ocean, and the planet's red color is a direct result of this oxidation, essentially the rusting of iron in its surface materials. Significant transformations also involve carbon dioxide, one of the most prevalent greenhouse gases in Earth's atmosphere alongside water vapor. Volcanic eruptions constantly release carbon dioxide from deep within the mantle into the air. Through a complex mechanism called the deep carbon cycle, this carbon dioxide is absorbed into the oceans, reacts with substances like limestone, and can eventually be cycled back into the Earth's interior. This means that global geological activity directly regulates the amount of atmospheric carbon dioxide, which in turn governs the planet's temperature. We theorize that Venus once had oceans, but because of its proximity to the Sun, its high surface temperature caused them to evaporate early in its history. Without oceans to participate in a carbon cycle, carbon dioxide began to accumulate in its atmosphere without any check or balance. This absence of a regulatory process led to a catastrophic buildup of greenhouse gases, a phenomenon we describe as a runaway greenhouse effect. These cases demonstrate that atmospheric changes on exoplanets, changes we cannot currently see or distinguish with our astronomical tools, can ultimately determine whether life is possible there. A planet in the habitable zone with very little water could easily suffer a runaway greenhouse effect and transform into a world like modern Venus. Yet from our distant perspective, it would be incredibly difficult to know if this had happened. Our solid understanding of how life began and evolved right here on Earth provides a crucial framework for discussing its potential development on similar planets. While the biochemistry of alien life might not rely on the DNA-RNA system familiar to us, it's a reasonable assumption that life elsewhere would also be founded on complex carbon-based molecules for encoding information. In Chapter 15, I'll delve into why carbon is uniquely suited for this role, but for now, it's enough to know that its ability to form stable chains and rings makes it perfect for building the intricate molecules necessary for life. To speculate on how natural selection might function on other worlds, you don't need to envision a galaxy filled with the bipedal, English-speaking humanoids of science fiction. Instead, we can analyze the rise of intelligent life and civilization on our own planet. By studying Earth's history, we can project how comparable processes might unfold on other Earth-like worlds throughout the galaxy, starting with the most fundamental principle: natural selection. Natural selection operates without any regard for lofty ideals like morality or altruism. To make this point to my students, I often tell an old joke about two tourists who stumble upon a hungry bear. One of them immediately starts taking off his heavy backpack. His companion asks, "What are you doing? You can't outrun a bear." To which the first tourist replies, "I don't have to outrun the bear. I just have to outrun you." It's irrelevant whether the slower person was a kind-hearted altruist. Natural selection only cares that the faster one survives to pass on their genes. So, what does this tell you about the kinds of life forms that might evolve in other habitable zones? The answer, I'm afraid, isn't very comforting. It is highly improbable that these beings would be any more noble or benevolent than Homo sapiens. When you reflect on our own species' history, which, according to paleontological evidence, includes the extinction of over 20 other hominid species, it's difficult to expect that any technologically advanced beings we encounter will be more peaceful than we are. Whoever we might find in the far reaches of space will likely be just as morally complex and warlike as humanity. This realization is quite unsettling. To truly appreciate its weight, imagine compressing the entire history of the universe into a single calendar year. On this scale, the solar system and Earth wouldn't form until early September, and the whole of human scientific development would flash by in the final few seconds of December 31st. It seems highly improbable that in this entire cosmic year, no other species attempted to explore science before we did. The laws of physics and chemistry aren't mystical secrets. Any reasonably intelligent civilization could uncover them, and at least some Earth-like worlds should have produced such a species. What makes this so troubling is our complete lack of evidence for any such civilization. Even if we assume that faster-than-light travel remains impossible and no major technological leaps are made, calculations show that humanity could populate the entire galaxy in about 30 million years, which is less than a single day on our compressed timeline. If we are capable of this, then any other civilization with similar capabilities should be as well. This brings us to the core of the puzzle known as the Fermi paradox. The great 20th century physicist Enrico Fermi, upon hearing a discussion about the millions of advanced civilizations that should exist in our galaxy, paused and famously asked, "But where is everybody?" In other words, why have none of them visited Earth? Why, as we search the cosmos for extraterrestrial intelligence, are we met with what has been described as the Great Silence? Scientists and science fiction authors alike, with their vast imaginations, have proposed numerous potential answers to this question. Among the most popular explanations are a few key hypotheses. The zoo hypothesis suggests aliens have designated Earth as a nature preserve, off-limits to interference. The Star Trek hypothesis posits a kind of prime directive, forbidding contact with less developed civilizations like ours. Then there's the paradise hypothesis, where contented aliens are so satisfied with their own perfect worlds that they have no desire to explore. And finally, the replacement hypothesis imagines that organic life has been supplanted by intelligent machines, which have no interest in making contact with biological beings like us. We could continue listing these theories, but you likely see the pattern. And while it is easy to imagine any one of these scenarios being true for a specific civilization, it is much harder for me to believe that every single advanced species in the universe would adhere to one of these restrictive paths. To grasp the significance of this, let's revisit the statistics from Chapter 1. Millions of Earth-like planets must exist in the habitable zones of stars. This is reinforced by the fact that we have already identified a couple of dozen such worlds among the few thousand exoplanets we've discovered. It is simply improbable that the inhabitants of every one of these planets would adopt a policy like the Prime Directive from Star Trek. We're confronted by the fear that the most direct answer to why we detect no signs of advanced alien civilizations is that they simply aren't there. The only explanation that the laws of nature seem to offer for this absence is a deeply unsettling consequence of natural selection. This reasoning suggests a truly bleak fate for the inhabitants of Earth-like worlds, as natural selection often results in the supremacy of aggressive species, much like Homo sapiens. It's plausible, therefore, that across cosmic history, countless planets have seen intelligent life evolve, only to annihilate itself upon reaching a scientific understanding of the universe, long before they could colonize even their nearest stars. This sobering thought offers the most straightforward solution to the Fermi paradox, and it's an idea that can send a shiver down your spine. However, it's important to mention that discoveries made in the study of the interstellar medium while I was writing this book suggest another possible solution to the Fermi paradox. This alternative is also founded on the fundamental laws of nature, just like the self-destruction hypothesis. In Chapter 17, we will delve into these new findings, along with a number of other unresolved questions. As my colleagues Mike and Jim would say, no matter how much we learn about life in the galaxy, you can be certain that within the next year, something entirely new and unforeseen will emerge. They believe it will likely be something so bizarre that we can't even begin to formulate a concept of it until we observe it directly. Imagine standing where the sun is fixed on the horizon. This isn't a fleeting moment. Here, the sun never climbs any higher. From your vantage point on a mountain peak, you can gaze down upon the sunlit portion of the planet, a scorched desert landscape deeply scarred by canyons. Then, turning the other way, you can peer into the profound darkness blanketing the planet's other half, where you might just discern the outlines of colossal mountains of ice. You are on the Terminator, a slender ribbon of land separating the eternally blazing day side from the perpetually frozen night side. And it is the only area where life can possibly survive on this world. Ferocious winds blow ceaselessly from the desert toward the glaciers, a constant and powerful force. You can see nearby wind power stations, constructed by the beings who inhabit this Terminator zone. If you observe the engineers and technicians servicing the generators, you'll notice their bodies are streamlined, and they move with a posture that seems to press them into the ground. This is how they must adapt to survive the furious, never-ending gales on the planet we call Nimbus. The worlds we've explored until now have had some familiar qualities, as Earth also has water, ice, and oceans. But the planets we are about to visit will seem far less recognizable. In this chapter, for instance, we will investigate worlds that are tidally locked, meaning they always present the same face to their parent star. This results in a sunlit side that is perpetually scorching, and the side facing away into deep space that is cold and dark. A transitional zone, a narrow nimbus encircling the planet, exists between this extreme heat and cold. That is why we have given our imaginary planet its name, Nimbus. We've all known since we were children that the moon consistently shows the same side to Earth. But have you ever stopped to think about what an incredibly precise coincidence that requires? For the moon to always keep one hemisphere turned toward Earth, it must complete one rotation on its axis in the exact same time it takes to make a full orbit around our planet. In essence, a lunar day has to be precisely as long as a lunar year. Any other relationship between its rotational speed and its orbital speed would mean that observers on Earth would inevitably see its other side. While this may sound like a rare occurrence, such situations are surprisingly prevalent throughout the galaxy. This state is known as synchronous rotation, or tidal locking. Within our own solar system, a great number of moons are tidally locked to their parent planets, while others exist in more intricate relationships, called resonances. It also occurs that a planet itself can become tidally locked to its star, particularly when the distance between them is relatively small. We believe, for instance, that all 7 of the Earth-like planets orbiting the star TRAPPIST-1 are held in this gravitational grip. For a time, scientists thought Mercury was also permanently facing the Sun, but more precise measurements of its rotation proved this assumption to be incorrect. As the name of this phenomenon implies, the Moon's constant orientation toward Earth is a direct result of tidal forces. We tend to think of tides almost exclusively in the context of oceans, and anyone who has lived near a coast is familiar with the two high tides that occur each day. When we hear the term tide, our minds instinctively picture the rising and falling of water, which we know is caused by the gravitational influence of the Moon and, to a lesser degree, the Sun. Yet, our planet also experiences earth tides, which are just as frequent as ocean tides but far less widely known. You might be shocked to learn that wherever you are, the very ground beneath your feet rises and falls by nearly 30 centimeters twice every day in what is called an earth tide, a phenomenon also caused by the Moon's gravity that we don't notice because it affects areas thousands of kilometers wide. To give you an idea of how subtle earth tides are, imagine if the surface of the continental United States were to rise by 30 centimeters over just a few hours. This would produce no sensation whatsoever. These tides can only be registered by exceptionally sensitive instruments. For example, scientists at the Large Hadron Collider in Switzerland must continuously factor in these terrestrial tides when calibrating their incredibly precise equipment. Since the Moon's gravity is strong enough to cause these tides on Earth, it follows that our planet's gravitational influence creates comparable tides upon the lunar surface, a process that ultimately results in tidal locking. The Moon's surface isn't perfectly rigid and possesses a degree of elasticity, so as Earth moves through its sky, the lunar crust responds to the gravitational pull by oscillating slightly. This gravitational interaction deforms the Moon, creating what we call tidal bulges. One of these bulges is consistently situated on the side of the Moon directly beneath Earth, moving across the lunar landscape as the Moon rotates. However, our planet's gravity also generates a second, less obvious bulge on the exact opposite side of the Moon. The simplest way to picture this is to think of Earth's gravity lifting a portion of the Moon's surface on the near side, while simultaneously pulling the Moon's main body away from its surface on the far side. Incidentally, it is this same two-bulge mechanism created by the Moon on Earth that explains why you experience two high tides in the ocean each day. You can visualize these two tidal bulges on the Moon as a pair of handles that Earth's gravity can grip to influence its rotation. If the Moon were to spin on its axis faster than its month-long orbit around Earth, our planet's gravity would effectively grab these handles and pull back, slowing the rotation down. Conversely, if the Moon were rotating too slowly, Earth would use these same handles to accelerate it, pulling it forward to speed it up. This gravitational braking and accelerating mechanism has been at play throughout the entire history of the Earth-Moon system. Over immense timescales, it brought the Moon's axial rotation into perfect synchronization with its orbital period, which is why it became tidally locked, forever presenting the same hemisphere toward us. This tidal locking phenomenon isn't exclusive to our solar system. It can occur anytime a smaller celestial body orbits a larger one, especially when the orbit is close and gravitational forces are powerful. A great number of the exoplanets we have found are positioned very near their parent stars, leading us to believe that at least some of them exist in a state of synchronous rotation. So what might conditions be like on such a world? The most profound effect of being tidally locked is that the planet's surface is permanently divided. The hemisphere facing the star is relentlessly scorched, while the opposite side is trapped in an endless, frozen night. This essentially creates a world that is half searing desert and half Arctic tundra. Between these two extremes, however, a transitional area must exist, a thin strip running from north to south where the temperature could remain in a range suitable for liquid water. If you were to stand within this transitional zone, you would be in an incredibly strange environment. The sun would be fixed on the horizon, perpetually balanced on the edge of a sunrise or sunset that never actually happens. Stepping a short distance toward the day side would place you in a hot desert, while moving slightly into the dark hemisphere would immerse you in freezing cold. Any life there would be confined to this narrow band of perpetual twilight, and it would be unbelievably windy. The second law of thermodynamics, a fundamental principle of physics, dictates that heat must flow from hotter regions to colder ones. On our own planet, the temperature difference between the tropical and polar zones, combined with Earth's rotation, gives rise to atmospheric circulation and major ocean currents. Phenomena like the Gulf Stream and prevailing winds are essentially Earth's constant effort to distribute heat and equalize the temperature across its surface. On a tidally locked planet, the temperature contrast between the day and night sides would be vastly more extreme than anything we experience, likely differing by hundreds of degrees or more. Although the specifics would depend on the planet's geography and its proximity to its star, this immense thermal gradient would inevitably drive a global wind system of unimaginable and constant ferocity. On our own world, the temperature difference between the tropical and polar regions is precisely what drives the circulation of atmospheric air masses and major ocean currents, in conjunction with the planet's rotation. You can view phenomena such as the Gulf Stream and prevailing winds as Earth's continuous effort to distribute heat evenly across its entire surface. Compared to the temperature gradients on Earth, the disparity between the day and night sides of a tidally locked planet would be staggering, likely amounting to hundreds of degrees or even more. While the exact conditions would depend on the geography of Nimbus and its orbital distance from its star, we can outline some general features of its global wind patterns. We can surmise that gas on the perpetually sunlit side would constantly heat up and rise, while on the eternally dark side it would cool and descend, establishing a planet-wide pattern of atmospheric circulation. At high altitudes, powerful winds would blow toward the night hemisphere, while closer to the surface, cold air currents would complete the cycle by returning to the day side. You would observe a similar type of circulation on Earth if our planet did not rotate, with warm air rising at the equator and sinking at the poles. This system is known as a Hadley cell, named for the British meteorologist George Hadley, who first theorized this mechanism to account for the trade winds. It's also worth noting that the United Kingdom's primary climate change research institute, the Met Office Hadley Centre, is named in his honor. If Earth's atmospheric movement were driven by temperature alone, it would be dominated by two immense Hadley cells. Warm air would ascend at the equator, travel north in one hemisphere and south in the other, and then descend over the poles. This would cause surface winds to consistently blow from north to south in the northern hemisphere, and from south to north in the southern hemisphere. However, the reality on our planet is far more intricate. Earth actually possesses three distinct atmospheric cells in each hemisphere: the trade winds blowing from east to west near the equator, the prevailing westerlies moving from west to east in the mid-latitudes, and the polar easterlies, which blow from east to west like the trade winds in the Arctic and Antarctic regions. The reason for this complex wind structure is Earth's rotation. The faster a planet spins, the more of these atmospheric bands will emerge. For instance, The numerous distinct bands you see on Jupiter are partly a result of its day lasting only about 10 hours. Nimbus, however, is in a state of synchronous rotation, meaning its spin is exceptionally slow, as it completes just one revolution on its axis for every orbit around its star. Consequently, you should expect its air mass movements to be governed almost entirely by the temperature differential between its two hemispheres. Moreover, the greater this thermal contrast, the more extreme the wind speeds will become. Calculations indicate that on a planet orbiting close to its star, these winds would probably exceed the speed of sound. Their Mach number could reach values significantly higher than any winds recorded in our solar system, leading to an atmosphere filled with all manner of local complications. Much like Earth's simpler circulation pattern is overlaid with phenomena like jet streams and hurricanes. The extreme temperature difference on Nimbus leads to another critical outcome. Any surface water on the day side would likely evaporate quickly in the intense heat. The resulting vapor would be swept by the winds to the night side, where the constant, deep cold would cause it to precipitate as snow or ice, burying the surface. This process implies that the planet's dark hemisphere would be encased in a layer of ice, its thickness determined by the world's total water supply. Recalling our discussion in Chapter 8 about water accumulation, if Nimbus has water reserves comparable to Earth's, its night side would be covered by a gigantic glacier, the size of a hemisphere and many miles thick. Should this planet also be large enough to sustain convection in its mantle, its dark side could closely resemble the world Iceheim from Chapter 6. In this scenario, plumes of hot magma could rise from the planet's interior, creating subglacial pockets of liquid water where life could, in theory, take hold. Everything we previously discussed about the evolution of life and civilization on Iceheim could therefore apply to this subsurface environment on Nimbus. However, the scorching winds of Nimbus introduce a unique factor, as they would persist even after a massive glacier forms. Near the twilight zone, the heat radiating from the day side could be enough to melt the edge of the ice sheet. If this were to happen, a narrow band of liquid water would form at the glacier's perimeter, creating another nimbus, a ring, around the frozen hemisphere. So, if you were to stand on the Terminator line, you would find yourself looking at a frozen tundra on one side of a narrow ocean and a scorched desert on the other. But honestly, you might be greeted by an even more magnificent spectacle. As ice builds up on the night side, it would begin to behave like our Antarctic ice sheet. Under the relentless pull of gravity, this ice would slowly flow outward from the center of the dark hemisphere, forming immense glaciers. Upon reaching the shore of the Terminator Ocean, these glaciers would break apart, calving massive icebergs into the water, just as they do here on Earth. Imagine standing on the shoreline of an ocean, with a scorching desert at your back, listening to the waves crash as you watch icebergs drift by in the water. The sight would be truly breathtaking. On Nimbus, powerful winds would generate two constantly opposing phenomena across its aquatic regions. They would dramatically speed up evaporation from the ocean's surface, carrying that moisture to the planet's night side in a process similar to how you might fan something to help it dry. At the same time, stronger winds would accelerate the melting of the glacier on the dark side, causing more water to flow back into the twilight zone. Depending on which of these two forces proved dominant, the amount of liquid water on Nimbus could fluctuate enormously. It might range from a deep sea that encircles the entire transitional zone to little more than a shallow stream in the hot desert that frequently evaporates completely. However, because our focus is on the potential for life to develop, we will proceed with the assumption that the planet maintains a continuous, ring-shaped ocean. Now that we have completed our standard search for water and have a good grasp of the peculiar natural conditions on Nimbus, let's turn to another potential feature of a synchronously rotating planet. One that could be vital for a form of life very different from our own. The silicon cycle. Here on Earth, we are very familiar with the hydrological cycle, where sunlight evaporates water from the oceans, which later falls as rain or snow, and ultimately returns to the sea. One of the most fascinating possibilities on a tidally locked planet is the existence of an analogous cycle involving minerals that contain silicon. Picture a world in a state of synchronous rotation, where the day side is so intensely hot that the rocks on its surface have melted. If these rocks are composed of silicon-bearing minerals, this could result in a vast ocean of molten silicon on the planet's illuminated hemisphere. To give you a sense of the temperatures involved, pure silicon melts at 1,414 degrees Celsius, while silicon dioxide, a very common mineral, has a melting point of 1,710 degrees Celsius. Some of this molten material would evaporate into the atmosphere, where winds would transport it to the planet's night side to freeze and precipitate. Essentially, it would perpetually snow silicon flakes on the dark side of the world. We can also envision geological processes, similar to the tectonic activity on our own planet, that would carry this silicon back to the molten ocean, thereby completing what you could call the silicon cycle in nature. We will delve into the specifics of silicon-based life in Chapter 15, but for now, it's enough to note that this silicon cycle could provide the chemical foundation for the emergence of an entirely new form of life, which we'll refer to as life unlike ours. Furthermore, recent theoretical calculations have uncovered another fascinating consequence of tidal locking and this potential silicon cycle. A study led by one of the authors, conducted by George Mason University student Probal Saxena, investigated how the accumulation of silicon snowflakes on the night side might impact the planet's rotation. The research suggests that if there were no mechanism to return the silicon to the day side, the buildup would create an effect much like an unbalanced washing machine during its spin cycle. This significant shift in the planet's center of mass would eventually break the synchronous rotation, forcing the world to start turning until its day side became the night side, and vice versa. What's particularly remarkable is that this process of escaping tidal lock would take only a few tens of thousands of years, whereas achieving that locked state in the first place requires millions of years. Consequently, some planets might experience constant gravitational oscillations. A planet could spend millions of years gradually settling into synchronous rotation, only for the shift in its mass to disrupt that state as soon as it's established. The most intriguing scenario would arise if the system's parameters were perfectly balanced. In that case, the planet might exist in a tidally locked state for brief intervals, but when viewed over timescales of millennia, it would appear to be rotating very slowly. This slow rotation would cause the habitable twilight zone to gradually migrate across the planet's surface. This planetary state is fascinating because it would subject the inhabitants of the twilight zone to continuous and novel environmental challenges. Many paleontologists theorize that similarly abrupt changes in our own world's environment were the catalyst for the evolution of intelligent life on Earth. For instance, as Africa's lush jungles began to dry out and transform into savannas, our ancestors who adapted to bipedalism gained a decisive advantage, allowing them to travel between forested areas more easily. This adaptation freed their hands for tool use and, as the hypothesis suggests, spurred a rapid increase in brain size. The inhabitants of Nimbus's shifting transitional zone would be confronted with challenges analogous to migrating across mountains and valleys. From that point, it isn't a huge leap to imagine the rise of intelligent life and sophisticated civilizations. On Nimbus, we are faced with a scenario that mirrors the water worlds from Chapter 8, where two potential centers for the origin of life existed. Here, one such hub could be the water bubbles near thermal vents under the ice on the night side, while the second is the Twilight Zone's ocean. We will now examine each of these possibilities in turn. In Chapter 6, as you'll recall, we examined how life, intelligence, and even technology could emerge in a setting bounded by ice sheets and thermal craters. My central theory is that on Earth, multicellular organisms originated around oceanic hydrothermal vents. I'm operating on the assumption that these same fundamental processes could unfold near similar vents on the planet Nimbus, raising the possibility that an advanced technological society, like the one symbolized by the pipe on Iceheim, might also flourish beneath the ice there. Now, let's consider what would happen when civilizations born around these thermal vents began to explore their surroundings. For the inhabitants of Iceheim, the only path of exploration was directly upward toward the ice's surface. The dwellers of Nimbus's vents, however, have another option besides going up. They can also travel horizontally to the edge of their world. This means they could breach the ice wall that isolates them from the Twilight Zone, a feat likely far easier than reaching the ice surface on the planet's dark side, giving them a clear route to colonize the ocean in that transitional region. Beyond that first scenario, it's also conceivable that life could have arisen independently in Nimbus's Twilight Ocean, just as some scientists theorize it did here on Earth. Despite its unique placement, this ocean could possess all the requisite characteristics for life to begin and evolve. While the constant, powerful winds might slightly modify the Miller-Urey process, there's no compelling reason to think they would prevent it entirely. Molecules from the atmosphere could be swept onto the ice and later enter the ocean as the ice melts, rather than dissolving directly into the water. Moreover, on a tidally locked planet like Nimbus, numerous versions of what Darwin famously called a warm little pond could form, providing ideal cradles for life's origin, even without the oceanic tides that help concentrate organic materials on Earth. When you look closer at life in this transitional zone, you realize its most defining feature would be the intense winds that blow relentlessly from the night side toward the day side. It's not hard to picture several strategies for adapting to such a relentless gale. For instance, organisms could simply live underground or remain submerged in the water. Any creatures that did venture onto the surface would almost certainly evolve streamlined bodies and move very close to the ground, perhaps resembling a kind of flattened beetle. The wind itself could even become an integral part of their reproductive cycle. We see on Earth how organisms like oysters use water currents to carry gametes, and wind pollination is common among plants. Likewise, life on Nimbus could harness the wind to scatter its reproductive material across the Twilight Zone. The constant gales could also serve as the primary energy source for any advanced civilization that might arise. It's entirely plausible that Nimbus engineers would invent wind power plants long before they ever developed the steam engine. They would also become experts in designing structures capable of withstanding these powerful winds. With that kind of protection, there is no reason they couldn't develop telescopes and an advanced astronomical science. The most fascinating speculation about life on Nimbus involves comparing the beings from under the nightside ice sheet with those that evolved in the Twilight Zone. Depending on the ice's thickness, organisms could develop that are capable of moving between these two distinct environments. For such creatures, traveling from the twilight zone into the subglacial realm might be no more challenging than it is for us to climb a high mountain from sea level. In this scenario, the ice dwellers venturing into the twilight zone would eventually cross paths with the twilight beings going about their lives. If my reasoning from the previous chapter is sound, that natural selection often favors more aggressive species, then these encounters might be far from peaceful. On the other hand, it's possible these two groups would possess skills that complement each other perfectly. The ice dwellers, much like the inhabitants of Iceheim, could be masters of mining and metallurgy, while the beings from the twilight zone would be adept at harnessing the planet's ferocious winds for energy. This could lead to a mutually beneficial coexistence, and in either case, the meeting of these two distinct forms of life provides a wonderful premise for a science fiction story.